Hey, it's Straw Hat Sam here, and in this video I'm going to be talking about PID tuning, specifically in the context of Cinelifters. So a Cinelifter is a term, I don't know who coined it, probably Andy Shan. Oh, and forgot to mention, as a disclaimer, even though I do have a mechanical engineering degree, I'm just one person. This is only one slice of my world experiences. There are many other people out there that, like for example, UAV Tech, Mark Spatz, his PID tuning philosophies or practices, I follow directly from that guy. And so watch his videos. A lot of this has inspired my thinking and my process. So check out his channel, of course, UAV Tech. So to get your brains ready to prime you, here's a quiz about Cinelifters. What are the factors that we must consider when doing the PID tuning process with a Cinelifter? Heavier payload, the fact that the camera is consuming power from the battery as well. Cinelifters must use higher voltage, and payload dynamics. So pause the video to figure out on your own which of these you must consider when PID tuning a Cinelifter. Okay, answer time. So heavier payload, that is definitely one of the choices. The reason why is because with a higher payload, there's more rotational inertia in the drone, and that mostly affects the P to D ratio. You need more D to compensate so that there's less bounce back coming out of turns and rolls. Okay, power camera consumption. Yeah, the camera is drawing like, I don't know, at most 2 or 3 amps, but that's not really going to be any kind of factor that we have to take into consideration. So that one's out. Higher voltage. Cinelifter must use higher voltage. This is not necessarily true. When I was using an X-class Cinelifter, I was running 8S instead of the usual 12, and it worked just fine. As long as your drone platform works and flies smoothly, then use whatever voltage you have to. Payload dynamics. This is a super important element that goes into PID tuning, and we'll talk more about this. So the two answers are heavier payload and payload dynamics. Notice how they both have to do with the camera payload. This video can be broken up into 3 main chapters: PID tuning, resonance, and design. If you stick around long enough, you'll get the good stuff at the end. Okay, so PID tuning, you're wanting to know how to pin your TUD. You're wanting to know how to tune your PID, your drone, and it's very important that you don't crash it, that you get any flyaways and all sorts of dangerous stuff like that, because it's a lot of money in the air. So I'm gonna give you a process here. First is hover at low PIDs. Now, in general, what I do is I use the sliders. Follow UAV Tech's slider tuning video. He PID tunes his drone in like 2 packs. That's the same process that I use. But with a Cinelifter, you want to be careful. Set your P to D ratio to like, I don't know, 1.8 is a good number, where you have a higher D turn than you would normally to compensate for the extra momentum of the camera payload. And then once you have that, turn down your PD gains such that they're in the like 30s to 40s. And what this will do is first, make sure your drone is actually, the propellers are turning in the right direction and all that stuff, so nothing crazy happens. But when your drone is lower in PIDs like this, if something crazy happens, like a flyaway, it's not going to have enough power or reactivity in order to actually take flight and shoot up into the air. So that's a safety thing. The second reason why you want to start off your drone with the Ps around 30 or 40 is checking resonance. You should really learn how to use black box, and there's plenty of videos on how to do that. Because the power of black box is you can go in there and you can see things that you can't normally sense. If you get really good, you can hear resonance and oscillation. It will just sound more rough around the edges, but you won't be able to really quantify that. So after doing a hover test, so first step, hover test, low PIDs, check the black box, search for any resonance spikes. And resonance spikes usually happen with either in the frame itself or with the camera payload mounting system. Okay, second step is to adjust any filters you have. So the way UAV Tech does his filters, I'm a fan of. What you do is you turn off the gyro low pass filters, and then you're utilizing the dynamic notch filter and the RPM filter to do all the filtering for your drone. And what that does is reduce phase delay. And you want to reduce phase delay as much as possible. We'll talk about that more in the next chapter. But the important thing here is if you have resonance because of your camera or your frame, you want to apply a notch filter. Okay, real quick, what a notch filter is this is a spectrograph, or I don't know what you call it, but it's in the black box. And what a notch filter does is you choose a center point. So let's say the center point for this one is 80 Hertz. And then you choose a low, what is it called? Like a center and then a cutoff. So let's say your cutoff is 70. What that does is it's like a little spear that when it's closer to 80, the notch filter becomes more powerful, and it tells the flight controller to ignore that frequency range. And that becomes very useful if you have resonance issues. Okay, we're still on PID tuning. The third part is start pushing those PIDs. Once your drone is flying smoothly and you're getting no oscillations or resonance, then you can start bumping up those Ps. Now, I found from my experience, the sweet spot is around 60 or 70 for the P turn, but obviously every tune is going to be different. Even if you have the same drone, even if you have different flight controllers with different gyros, you're going to have a different tune. And as far as PID tuning philosophy, it's a matter of what you value. So this is like a spectrum of what you could do with your PID tune. You could have something that puts more emphasis on smooth, like smooth flight footage. So that's especially important with Cinelifters. Or you could put more emphasis on control. Now, little quiz, which of these correlate with your PID tune? Higher PIDs mean which of these? Either smoother or more control. If you chose control, that's correct. When you increase your PIDs, that increases the power that's going into the motor so it can turn those propellers and react to external forces. The problem with that, though, is if your PIDs are too high, your motors become more reactive. And the D term plays a large role in having overly reactive motors. They get hot, they make weird noises, and what's happening is there's feedback in the system, like resonance. So if your PIDs are really high, you're going to have good control over your craft, and this is something that FPV racers like, something that's responsive and feels locked in and agile. The problem with that is that as you increase your PIDs, your motors become more reactive to all sorts of things, to the wind, to resonance in the frame. On the other end of the spectrum is valuing smoothness. If your PIDs are lower, your footage is going to be cleaner. So the motors aren't overly reactive, they're just doing mostly their job of maintaining thrust. But motors need to push the prop responsively enough so that it can maintain attitude. Attitude is the tilt of the craft. So if the PIDs are too low, then you're not going to feel totally in control. It's going to feel a bit loosey-goosey in the air. And the goal with Cinelifters is to find that balance point. And that's really up to you. If you need pristine footage, you might have to do it at the cost of less agility and control of your craft and get used to flying with something that's a little bit more loosey-goosey. That may be the case if you use something like SteadXP, which is very sensitive to any kind of vibration. But at the same time, you want to be able to control your craft So pushing your PIDs up will make it feel a lot more locked in. Okay, next let's talk about resonance. I have the pigeon here as like a prop. Resonance, it normally occurs in drones throughout the frame, you know, in the sandwich plates that are holding the flight controller and all sorts of stuff like that. But with a Cinelifter, you have this camera payload. So resonance is something that can happen in normal drones just within the frame itself. Because these frames, they're not perfectly stiff. They can bend in like a U direction like that. They can bend in like an S direction. And these are called harmonics. As you go up and up a harmonic, they become higher and higher frequencies of resonance. And so those are things you definitely need to consider. But in the context of Cinelifters, there's an added factor, and that's this camera here. So oftentimes it's the lens that's the culprit. It can shake up and down. Even if you have like a rigid mounting system, there's always a little bit of play, there's always a little bit of springiness to a rigid mounting system, and it will bounce up and down. And whatever that frequency is, it may cause issues because your drone has natural frequencies not just within the frame itself, but as a platform itself, because the motors are spinning the props are creating thrust, and the whole drone itself has a angular momentum. So if you have big chunky motors and really wide arms, you're going to have a higher rotational inertia, so it's going to be harder for it to oscillate back and forth. So that means the drone's resonance frequency is going to be lower. So maybe it's like, I don't know, 30 hertz or something. But as your drone gets smaller in footprint and it's lighter, then it can oscillate at higher frequencies. But thrust also has to do with it too. If you have like a ducted Cinewhoop, although it's small and compact and small motors, the thrust that it produces is very small compared to the payload. So that influences the resonance of the drone platform as well. The issue usually with Cinelifters is the first harmonic resonance of both the camera and the drone itself. Basically, when these two things equal each other, the rate at which the drone likes to do this, and the rate at which the camera likes to shake up and down, like, usually it's the roll axis that doesn't give a lot of issues, but it really depends on your mounting system. So when the rate at which the camera likes to jiggle up and down and the drone likes to bobble, you have a problem there. That's called resonance, and you can get a flyaway if your mounting system is not very rigid. So like an example of flyaways, I had a drone that had wire rope isolators, and they worked great, but the issue was the resonance frequency of this camera payload, the rate at which it rotated on the roll axis was very similar to the frequency at which the drone liked to oscillate on the roll axis. And I ended up getting like 3 flyaways with this drone, and that's also, I caught it twice, but the third time I didn't catch it and I broke my camera. So that's why it's important to follow the steps in the PID tuning guide and start off with low P values. So if you do have resonance, you're not going to get a flyaway, and you're not going to have to run after your drone and catch it with your bare hands. After disarming, of course. Next is the filters you need to consider in order to mitigate resonance. As UAV Tech has shown very effectively, turning off your gyro low pass filters and letting the dynamic filter and the RPM filter do the filtering for your drone is good for Cinelifters. The reason why is because it reduces phase delay. Phase delay, the way it's linked to resonance is as you increase phase delay, in your PID loop of your drone, you increase the reactivity. So what is phase delay? It's the responsiveness of the flight controller. How little time does it take to respond to external forces acting on the flight controller trying to change its angular attitude. Reactivity, what I'm calling it, is the chances of a drone having resonance of any kind. And so as you increase the phase delay, the drone it's going to take more time to react. It's going to be less responsive to external forces. So with a payload like this, it's acting like an external force on your flight controller, which is mounted usually in the center of your drone here. And if it has a lot of phase delay, when this payload starts swinging back and forth, it's not really swinging, it's only like vibrating really. The flight controller is going to react, but it's not going to react in time. So it's like someone trying to stop a child that's swinging. If you are not responsive enough and you don't press against the child as they're coming toward you at the right time, then you might actually be too late, and by the time the child is swinging back, you'll hit the child, you'll push the child, and they'll swing even more, and it gets into this runaway feedback loop. And so you want to reduce phase delay as much as possible, and that means tailoring your filters as such. So lose that low pass gyro filter, use RPM and dynamic filtering if you're using Betaflight, of course. And then I usually keep the D-term filters, like the slider, to medium. Okay, so another quiz for you. Here's a spectrograph that I drew that looks like what you would see in Betaflight black box. This spike here, what is that? KSSO? Would it be motor vibrations? B, loose wire, or perhaps an antenna rattling about? A faulty gyro? Or D, resonance? Which of these? So pause the video, think about it, take your guesses. The answer is D. When you see something like this, especially in the frequency range of 30 to 80 hertz, around that range, that usually means that's camera payload resonance. So how do you deal with that? There are two main things you can do. One is make sure your filters are sorted out. Try having taken off the gyro low pass filter and utilizing the other like dynamic notch filter, RPM filter, all that stuff in order to reduce the phase delay. The less phase delay, the more chance it's going to be able to react in time to whatever's going on with the camera payload and not freak out and cause the spike like this. Another thing is you can lower your PIDs. The lower your PIDs are, the less reactive the drone is going to be to outside forces, including camera payload resonance. Now you have to strike a balance, like if you, the big thing here with filters is the notch filter. So with a notch filter, you can just kill this thing and your drone will fly smoothly and you're done. The issue though is it depends on the situation. What if your PIDs are already very, very high? What you can do is instead of throwing a notch filter on there, you can lower your PIDs and maybe this spike here will turn into a little hump. And if it's a hump like that, it's not going to affect your footage. You're not going to notice any difference in flight performance. But if your PIDs are so low in order to get to this point that you feel like the drone is kind of loosey-goosey and slightly out of your control, then you might want to consider throwing on a notch filter. Now, the notch filter isn't the greatest solution because it does reduce phase delay or it does increase phase delay in the PID loop system. So that means the drone isn't going to have as good as prop wash handling, and it might have more chances of getting resonances at other frequencies, perhaps if there are other frame resonances. And the way that the notch filter works is you set your center at your cutoff, your center notch filter right at the peak of the spike, and then you want your cutoff to be a little bit of a factor of safety to the left of the spike. And you can find those points using the spectrograph in black box. And then so it starts here and it increases until it gets to the center point, and then it mirrors that curve once again on the other side. And after you apply the notch filter, you'll notice the next time you fly, this spike just completely goes away. And it's a little counterintuitive because, like, right here we have motor noise. This never goes away. There's nothing you can do about it unless you like switch your motors, I don't know, smoother bearings. You can reduce this a little bit, but it's always going to be there. It doesn't just like magically go away. But with resonance, it does magically go away. And the reason why is because as soon as you put that notch filter on, you're telling the flight controller, okay, ignore this frequency of vibration. Because the fact that the flight controller was not ignoring it before means that it was overreacting in this feedback loop that was causing the spike in the first place. So because you applied a notch filter, that vibration, that oscillation goes away completely. So it works like magic. The trick is, depending on what kind of lenses you're using, you need to find a notch filter that can accommodate a range of lenses that you know that you're going to be using. So the lighter your lens, the higher frequency the spike will be. The bigger your lens, the lower frequency this spike will be. But you want your notch filter to be able to accommodate this range of frequencies. But it actually doesn't vary that much as much as I've drawn here. Depending on your lens, it doesn't actually affect the resonance that much. So in contrast, this mountain over here, the motor noise, which never goes away, you can reduce this by lowering your PIDs, and that will cause the drone to be less reactive in general, because the motors can react to themselves. The vibrations that the motors produce, especially the D term, it will become sensitive to that, and the motors may make like a grinding noise. This usually happens with like ultralight frames, especially when there's a lot of resonance in the frame itself. But even just there can be issues within the motor, and lowering your PIDs will smooth out this mountain, but you don't necessarily need to do that. You can just rely on the RPM filter and the dynamic notch filter. And this graph here, I forgot to mention, this is like gyro scaled. This is the information coming into the flight controller before the filters have been applied. So that's why it's a little counterintuitive that this camera payload resonance spike would go away even on gyro scaled. It's because the vibration is actually gone. But after applying the filtering, then this mountain will flatten out and you'll be good to go. And but I'm just saying that as you increase your PIDs, you're increasing the likelihood that you'll get not smooth footage, because there's more chance for the drone to become too sensitive and overreactive. Okay, so I've been dancing around this topic of design for a while because it's my jam, and it's a bit controversial too as far as drone design. Everybody has their own artistic style and the way they design things. So do what you do, and this is just my perspective here. First, let's talk about, I want to get at something that there's a lot of debate on, is flight controller screws through the arms or not. I drew what I do above. I put the flight controller screws through the arms. Other people, many other people, they have the arms spread out and the flight controller is mounted to the sandwich plate. I drew mine slightly bigger because I am slightly biased toward my own design instinct. So sorry about that. The reason why I do this is because I want the flight controller to be mounted to the most rigid part of the frame possible, which is going to be the very center. And the closer these arms are together, like right in the center, the more meat there is, the more rigid of a connection there will be between the screw and the arms. So, you know, the motors, all these vibrations are coming into the arm, and sure, it's got a direct line to the motors, and it's going to see everything. It's going to see all those tiny little high frequency vibrations, But that's just it. Those vibrations are going to be high frequency. When vibrations are higher frequency, it's easier to filter them out because they're further to the right on that spectrograph on the black box. And as you apply low pass filters or whatever kind of filter, those are going to be easier to attenuate. And the style where you are mounting your flight controller on a separate, like a sandwich plate, and your arms are spread out, the reason why I don't do that is because of, I'm going to call it drumming. So like how a drum has a cylinder and then some kind of thin membrane, it produces noise because that membrane is oscillating up and down like that. So to some extent, drones can do that as well. This sandwich plate can vibrate up and down like a little speaker, and although it's the same amount of vibration coming in from the motors, exact same setups, the reason why this can drum is because of resonance. This little carbon fiber plate has its own resonance frequencies, and there's more chance for resonance of a higher amplitude to occur. It's that high amplitude, low frequency resonance that becomes an issue, as we talked about with resonance and camera payload oscillations. So, although the source, the vibration is the same, this one I think will fare better because although there's the same amount of vibrations, it won't resonate. Yeah, that's a word, right? It won't resonate as much. Well, with this flight controller setup, there's more chances that it will resonate. You might get lucky. You might have a flight controller that's mounted in this configuration and you have no problems. It just so happens that your motor setup, all the geometry lines up so that it doesn't get excited by these vibrations. It doesn't go like boom, 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 boom. But on the other hand, you may get unlucky and your flight controller area will resonate according to what kind of motors and props you're using. So just putting the flight controller screws through the stack makes it as rigid as possible so that the vibrations that are coming in are going to be as high of a frequency as possible and less chance of resonance. Okay, more on the aspect of just the frame in general. A stiffer frame is better. Why is that? Don't you want something that's lightweight so you have higher power to thrust ratio and your quad is more powerful and faster, maneuverable, and all that good stuff? That's all true, but it's, once again, like engineering in general, it's all a balancing act, and it's all about doing what's good enough. You're never going to get perfect. So this is like a very rigid, stout frame. This is a very thin frame. The advantage of having a stout frame is that the resonances that can occur are going to be of a higher frequency than the thinner one. So the rate at which this oscillates, kind of like versus something like this oscillating, this is going to oscillate at a lower frequency and this will oscillate at a higher frequency. So it's good to have your resonances be. So drone frames are so complicated. In my opinion, it's not worth really doing FEA analysis and mathematical simulation unless you're like really gifted. It just comes down to just building the damn thing and then testing it out to see if it works. Because drone frames are so complicated, there's like thousands of ways that they can resonate because the geometry is so complicated. In addition, having a thin frame, not only is it more susceptible to lower frequency harmonics, but it's also more susceptible to higher frequency ones as well. Like with an ultralight frame with big motors, it might resonate at like harmonics of like, 2, 3, and 4, and you'll get resonance issues not just within the first mode of vibration, but with all sorts of other modes of vibration. And then probably the biggest reason why you want a rigid flight controller is to reduce mechanical delay in the system. As the motor is producing thrust and like changing the attitude, the stiffer this frame is, the less delay in the mechanical system, and the sooner the flight controller is going to sense that change in angle. If you have something that's thin like this, the flight controller is mounted here, and if the frame is not rigid, it's going to bend a little bit, before the flight controller actually moves. And when that happens, there's delay in the system. And anytime there's delay, there's more chance of getting resonance. Okay, another aspect of Cinelifter design is how you're mounting the camera. So for this little explanation, I'm going to be talking about the pigeon. So it's got this rectangular box sitting on top of an X-frame. The first version of the pigeon, it flew fine. You can watch the video. It's called like Le Pigeon Maiden Flight or something like that. The issue with that is I couldn't push the PIDs too high. The reason why is the mounting points for the gummies, the alpha gel gummies holding up the payload, they were mounted directly into the arm, which is good because it's a very rigid point, and that's a place where the arm is not going to be bending a lot. So you want to mount your camera to the most rigid points on the drone as possible. But the issue is that the direction, the pitch direction, the longitudinal direction, these alpha gels were too close together in that direction. And so that meant that if I pushed the PIDs too high, the drone would become reactive in the pitch direction, and I would get camera oscillation where it does something like this. Like, this is the drone, this is the camera, and it's going like wow, 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 wow. And that was the problem with the first version of the pigeon. So 8 versions later, I eventually came to something like this, where all it was is just the damping washers or bushings were spaced out further apart in the forward and back position. And what this does is it raises the frequency at which the camera payload oscillates in the pitch direction. So for reference, here's the drone, this is the pitch direction. And you can see that these damping plates are much further apart in the forward and back position. So because it's raising the frequency of the camera payload resonance frequency, that allows you to push the PIDs a bit higher because the frequency at which the drone oscillates is a little bit lower. And the frequency at which the drone oscillates in the pitch direction is a little bit lower than the frequency at which the camera payload or even the lens oscillates up and down. So in general, it's good to just have your mounting points be further spaced in the longitudinal direction for cameras that have like lenses sticking out the front. Previously, I touched on the concept of like the rate at which the drone oscillates versus the resonance frequency of the camera payload. If possible in a design, you want to separate those as much as possible. Possible. The reason why those 5-inch mini quads, when people strap a DSLR to a 5-inch mini quad and not have issues really, is because the rate at which the big old camera on top oscillates relative to the frame is very low, like maybe 20 or 30 hertz. But the natural frequency of the drone itself, its ability to oscillate back and forth in either the pitch or the roll direction, is somewhere here. And if that's the case, if these two frequencies are spaced further enough apart, you won't get a resonance peak. Maybe you'll just get something like that. But as you approach closer and closer, if you match the drone to the camera payload frequency, that's when that little mound can become a dangerous spike. And in that case, you just need to apply a notch filter. So it's not really a big deal, but you just have to know what you're doing. Another example is my Beast class Cinelifter on the other end of the spectrum from my 5-inch example with the big DSLR. With a Beast class, it's super wide, you've got these big chunky motors, and the rate at which it is even able to oscillate is very low. It's like, I don't know, 20 hertz or something like that, 30 hertz. Yet my camera mounting, in some cases I use just a ball, like a ball head mount for the camera, no damping at all. In other cases I had a ball head mounted on this spider thing that had alpha gel gummies on it. The rate at which the camera oscillated on those things was like 50 or 60 hertz. And so it was the opposite of this. They were switched around. So the drone resonates at a low frequency, and then the camera resonates at a high frequency. And they're separate apart enough that resonance between the two systems doesn't occur. Like the money shot design, what's great about that design is that the camera mounting system is very rigid. It's got this aluminum adjustable thing, and it's got a whole bunch of these alpha gels, and the camera, it's just like, you know, solidly fixed to the frame, while the frame itself and the motors and the props, the rate at which it oscillates is probably pretty low. And so that way they probably don't even need notch filters for their rig, which is great because that reduces latency in the flight controller loop, so you get better prop wash and things like that, but at the cost of having a heavier drone. And then the thing about like notch filters, you know, they do reduce latency and reduce the ability to handle prop wash and things like that, and also like responsiveness to wind. With an X8 platform, and that's, I don't have one any I can show you that aren't top secret, but with an X8 platform where you have 4 motors on top and then 4 motors on bottom in an axial configuration, those have some kind of intrinsic aerodynamic handling abilities that make them very stable. And so even if you do have a notch filter, the flight performance is not going to be affected all that much actually. And I've tested this even with like very skilled pilots that can really feel out a drone. Oftentimes you can't feel a difference with an X8 drone that's properly designed with a nice stiff rigid frame and all those things accounted for. Okay, so back to like the most important part of this video is like actually tuning your Cinelifter craft. In summary, the first step you want to do is lower your P gains, set your P to D ratio around 1.8. You can play around with that as you raise your PIDs later and check for like bounce back on these sharp stick movements. And you want to be checking for oscillations. So do a hover test, then bring it back in, check the black box. Now, even if you can hear oscillations, that doesn't mean you're going to be able to detect at what frequency they're occurring. So that's what black box is for. Take a look at black box, see if there's any oscillations. If you're not, you're in luck. Your system is good to go. Now, step 2 is if you do have a notch filter, apply it, add a little factor of safety to account for any kind of differences in lenses you'll be using, and then make any filter adjustments. So like a lot of these Cinelifter frames, they've got very stout arms and things like that, and oftentimes you don't need the gyro low pass filter. But that's not every frame. You may have a frame, it might even depend on like who builds the frame. You might have a frame that is sensitive enough to necessitate a gyro low pass filter, and you just use the filter slider and then just slide it whichever way you need to in order to make it so you're not having weird noises and things like that. And definitely use black box all throughout this process. So for like the third step, incrementally raising your PIDs, what I do is I do a hover test. Okay, let's say I have resonance. I apply a notch filter, I do another hover test. No resonance, flies smooth, but it's a little loosey-goosey. So I start raising the PIDs incrementally, usually 1 or 2 steps on the slider at a time in beta flight. And then I check the black box again. I'd like do a hover test, check the black box, make sure that resonance spike hasn't spilled out the side of your notch filter, because that can happen too if your notch filter isn't wide enough. So make sure that's not happening. You can also tell just by hearing, like it doesn't sound as smooth. And so every time you raise your PIDs, do a hover test, make sure there's no oscillation. Once you get your PIDs up to like 50, 60, 70, I prefer around like the medium 60s. Once you get your PIDs up that high and you feel like you're in control and you've done a little bit of those jerk movements like UAV Tech or Stinger Swarm recommends doing for PID tuning. Basically, it's that step input process. As soon as you do that and you feel in control, then you can throw the goggles on and start flying. One thing I want to mention is like this kind of process, the hover test and all that stuff, it really helps if you know how to fly line of sight. So if you don't know how to fly line of sight yet, try practicing with a smaller drone in order to get comfortable taking off from the ground line of sight, landing, hovering, even doing a yaw with the drone line of sight. That will help a bunch so that you can test your platform safely, because you're going to be able to react a lot easier in time when you're flying line of sight if a flyaway does occur. As you're raising your PIDs, definitely use your senses, your hearing, your touch, feel the motors, listen. If something sounds off, something probably is off, as confirmed by black box. And once you get your drone in a controllable fashion and you're getting smooth footage, then you're pretty much good to go. So I'm just one guy. Although I have a lot of experience building drones, especially when it comes to cinelifting, I'm just one perspective. So please comment and share any kind of opposing viewpoints or things to add to what I've presented so far. And hopefully we can all learn some more about this cutting edge field in the drone industry. In other news, I moved down to Los Angeles for a new job as a cinema FPV drone designer. I can't share too much right now, but things will be happening in the future, so stay tuned for that.